Hello and welcome to today's webinar, Introduction to 3D Sand Printing for the Metalcasting Industry. We will begin the webinar in approximately 5 minutes. Thank you. Hello and welcome to today's webinar, Introduction to 3D Sand Printing for the Metalcasting Industry. We will begin the webinar in approximately 3 minutes. Thank you. Hello and welcome to today's webinar, Introduction to 3D Sand Printing for the Metalcasting Industry. We will begin the webinar in approximately 1 minute. Hello, and welcome to today's webinar, Introduction to 3D Sand Printing for the Metalcasting Industry, hosted by Modern Casting and Metalcasting Design and Purchasing magazines. I'm Al Spada, Vice President of Business Development and publisher of Modern Casting and Metalcasting Design and Purchasing magazines. I'll be your moderator for today's session. Today's speakers for the webinar are Steve Murray and Dave Rittmeyer from Hoosier Pattern. Steve has been using 3D printing in support of the metalcasting industry since 1993. He has been a presenter for various rapid conferences and the Additive Manufacturers Users Group. Training and mentoring the casting community about additive manufacturing throughout North America is a major commitment of Steve's. Dave has worked throughout Hoosier Pattern as a certified journeyman pattern maker, growing professionally within the company. As customer care and additive manufacturing manager, Dave works well to make sure the customer needs are met in a way that is beneficial both to Hoosier and its customers. While today's webinar is about hearing from the experts in the field of 3D sand printing, we also want to make sure we hear from all of you in the form of questions. To ask a question during the webinar, please look to the right side of your screen and locate the Go-To Webinar control panel. On it, you'll see a section called Questions. Click on the plus sign and then just type in your question in the available space. I encourage you to submit questions at any time during the webinar, and we'll be responding to as many as we can during the Q&A session after the presentation. What we can't answer on air during the webinar, we'll do our best to answer over the next few days. Also, please note that today's webinar is being recorded, and we will send a link to you by the beginning of next week so that you can view or share today's event as an on-demand viewing. Thank you to everyone for their attendance today, and with that, I'm going to turn the presentation over to Dave and Steve for this morning's webinar.
Morning, Al. Thank you. Hello. Well, we're going to talk about 3D sand printing, and we'd like to know, first of all, how many people out there listening to this today have used 3D sand printing to make their castings. And if you have, just go ahead and answer the poll question when it pops up on your screen. We're going to talk about 3D sand printing for foundry use. But first of all, we're going to have to cover a little bit of background on 3D printing in general, and then we'll jump right into what you need to use 3D sand printing in your foundry. Lastly, we'll cover how to apply what you're learning about 3D printing for your specific foundry needs. So let's get started. So when we hear 3D printing, rapid prototypes, rapid manufacturing, TCT, which is shorthand for time condensed technology, and I'm sure there's many other names being used in literature, they're all referring to the same thing, and that is additive manufacturing, or AM. There are only 7 recognized separate and distinct AM processes according to the ASTM. You will find that many of the machine manufacturers make up new names for the way their machines work to separate them from their competition. All of these ASTM recognized processes are capable of being used in the foundry in one way or another in production of castings. It is up to you and your team to figure out if that makes financial or engineering sense to use them. So let's take a quick look at all 7 of these AM processes to give us a reference from which to discuss this subject. The first is going to be vat photopolymerization. It is an additive process where a vat of liquid photopolymer resin is cured through a selective exposure to light via a laser or a projector which initiates a photopolymerization and converts the exposed area to a solid. This process is also called by other names that are trademarked by the machine manufacturers. Most of them we've heard of. SLA, which is stereolithography apparatus. DLP, digital light processing. 3SP, which is spin, scan, and selectively photocure. And the new one that's out is called CLIP, continuous liquid interface production. The VAT photopolymerization process can get you a high level of dimensional accuracy and produce very complex builds. You're able to produce a part that has a very smooth finish and a relatively large build area. One of the drawbacks is all the materials for this process are UV curable photopolymer resins. But this process can be used in the foundry to make consumable patterns for investment casting, and it can also be used to make foundry tooling for short run. With ingenuity and a little creativity, a pattern shop can add this additive process to their tooling arsenal. One of the older ones, people remembering back in the day, is sheet lamination. It is the process where sheets of material are stacked and laminated together to form an object. The lamination method can be chemical, adhesive, ultrasonic welding or brazing, and the unneeded regions are cut out layer by layer and removed after the object is built. This process goes by the names of LOM, L-O-M, laminated object manufacture, SDL, selective deposition lamination, and UAM, ultrasonic additive manufacturing. The new company on the block is MCore Technologies, and they make a number of the machines in various sizes that are doing this again. And this process is very good for making foundry tooling. The question comes up, and where it hit a wall was, it really doesn't compete very well with CNCs in speed of producing the tooling. The next is material extrusion. This process, material is extruded through a nozzle. The materials are heated thermoplastic materials, similar to a hot glue gun. This process goes by the names of FDM, which is fused deposition molding, and FFF, fused filament fabrication. The materials are inexpensive, and the machines are relatively inexpensive. And they can use multiple colors, and they can be used in a non-industrial environment, which means they can be in your home or office. The thing to remember on this is the materials going into this are thermoplastics, and they have been used in the foundry to make foundry tooling. Powder bed fusion is our next one. It is where a powdered material is selectively consolidated by melting the powdered material together by a heat source, such as a laser or electron beam. The powder surrounding this consolidated part area acts as a support, so it can make overhanging features, which is very, very cool. This process goes by a number of different names: SLS, selective laser sintering; DLMS, direct metal laser sintering; SLM, selective laser melting; EBM, electron beam melting; SHS, selective heat melting; MJF, multi-jet fusion. The strength of this additive process is that it can produce a high level of complexity through a wide range of materials. Materials used in this process can be some plastics, some metals, ceramic powders, and sand. This process has been used in the foundry to make mold loose pieces and consumable ceramic cores. Material jetting is where droplets of material are deposited layer by layer to make a part. The common varieties of material jetting include photo-curable resin and molten material that solidifies at ambient temperature. So these materials can be photopolymers, polymers, and waxes. They go by the trade names of Polyjet, ProJet from 3D Systems, SCP, which is smooth contour printing, MJM, multi-jet modeling, and you can get a very high degree of accuracy and full color parts. And you're also able to get multiple materials in a single part. This is huge. The main thing that foundries use this process for is for consumable patterns for the investment foundry. Directed energy deposition is the additive process where a powder or a wire is fed into a melt pool, which is generated on the surface of the part, where it adheres to the underlaying part layer by layer, and you're using a heat source such as an energy source such as a laser electron beam. If you really want to think about it, it is a form of automated welding. This additive process goes by the trademark names of LMD, laser metal deposition, lens, laser engineered net shaping, DMD, direct metal deposition. This process is not limited by the direction or axis. It can be very effective for making repairs. You take this process, add it into a tool changer on a CNC machine, and you got a heck of a hybrid approach to manufacturing. The last one we're going to talk about is binder jetting. This is what we use extensively with our sand. It is an additive process where a liquid bonding agent is selectively applied onto a thin powder material layer by layer. These binders can be organics or inorganics. If a metal powder is printed, they are typically fired in a furnace after they are printed. If ceramics are printed, then the end use will determine if the part needs to be fired or not. This process goes by trade names as 3DP or 3D printing, and machines are made by X1, VoxelJet, Veritas, and Tinker Omega and 3D Systems. They can also allow for full color printing. A high productivity rate and the ability to use a wide range of materials such as plastics, metals, ceramic, glass, and sand are some of the advantages for binder jetting. The foundry uses for this additive process is to make sand molds, cores, and perishable patterns for investment casting. Now, if you would like a quick cheat sheet on these 7, email Dave or myself, and we'll send you a copy of those cheat sheets to keep on hand and to share with others on your team. Now let's talk more specifically about the additive manufacturing of 3D printed silica sand for use in the foundries. This is a short animated graphic from 3D Systems. I'm sorry, from X1. Oh, I'm very sorry. I didn't mean to do that, from X1. And it's showing how the sand is mixed with an activator. It is then gone through and spread onto the machine in a thin layer.
And right now you can see there's a job box going in. You can see where it filled into the recoder, and here in a second I'll show you actually laying the layers. So every time it prints a layer, that box actually drops 10 to 11 thousandths. So there's a layer. It'll lay a base layer, and then it'll come back, and print head goes back and forth. It's kind of like printing a book report. You know, you need a whole sheet of paper to print out one picture or one paragraph. Same thing with any of the sand printers. You still need that full layer. So it goes back and forth, and then once it's done with that pass, or that layer, I should say, the print box will drop, and then lays another layer, print head comes back, and you can see the layers as it goes. So it just continuously builds, and currently with the S-Max that we have, anywhere from 19 to 21 hours we can fill that job box.
Okay, on a smaller scale, this is how this is working. You have uncoated sand particles. You're going to put an activator onto them. It's ready for printing. And then the binder is applied, and it adheres the group of sands particles together on that layer and to the layer below. So the droplet formation comes down, hits your powder, we're saying sand, penetrates, and that little glob that is hardened is now called a voxel. And that's why some of these different companies will have voxel in their name, because of how these are formed.
Yeah, and here's what some of our test results, what we're averaging here lately, for actually not lately, for quite a while now. We're averaging a permeability with printed sand of about 150 or so. LOI is running about 1.3%. We test X, Y, and Z bars, do a 5-piece average for every job box that's built. Where we're averaging about 320 newtons per centimeter squared for the X and Y. Z's are always a little bit weaker due to because of the layers, they're always a little bit weaker, so there's a little bit lower strength on those. And currently we're using an 83 GFN sand grain is what we're using.
We'll be happy to share these test results with you or send you coupons for you to verify in your sand lab. And here's some pictures of our sand lab and our operator checking them. The one on the right, Dave?
One on the right is a scratch test, so you have a non-destructive test. Foundries use it now. But it's just a telltale sign if your cores are weak or overly strong. Just gives you an idea. One on the left, we're weighing the bars. We always weigh them. Make sure they're the right weight range. Make sure they're not too dense.
Okay, now we're getting into the specifics of what we really came here for. We can give a preliminary quote from a 2D drawing, but what is really required is a 3D CAD model to produce a good quote and to print sand. New cast parts are designed with solid modeling, and so the CAD files are available, no problem. Older parts or legacy items could prove more difficult. If a drawing exists, then a solid model could be made from that. But remember, someone will need to sign off on this generated model. Any interested party, that being you, us, or a third party that you hire, can generate this model for you. Another way to get a CAD model is to laser scan the tooling or casting and take that data to generate a solid model. This is called reverse engineering, and it can be a more complicated way to generate a CAD model. There is no Staples easy button on this way, and it can require quite an investment of time. And again, you will have to have someone verify the model that is created. So how many printed products are you going to need? These can be mold packages or just cores. Are you thinking you're going to produce all good castings with no scrap? How about sample castings for testing? So get your number of castings you think you're going to need at the start. Coming back later can be an issue on timing. The other thing is casting simulation or solidification. It should be run. Again, this can be run by you, by us, or a third party. It is important to perform this calculation to enhance your chances of successful outcome. We don't want to cast and pray over a casting and hope we get it. We want to be guaranteed that we get a good casting every time we pour into a 3D printed mold. Last on our list is to know when you need your sands. Like FedEx, the faster you need it, the more it costs. So in all things, prior planning prevents poor performance. Let us know what your expectations are right from the beginning so we can meet them.
So we have the print envelope that we have is say 71 inches by 39 by 27 and a half. And a lot of people do castings larger than that or need molds larger than that. We've been asked many a time, can you do larger items? Absolutely you can. To do this particular impeller, it was going to take 4 different prints and we'd piece the cores together. We've done other projects where the core is 100 inches long and it's literally bolted together. So you can go large. It's like playing with Lincoln Logs or Legos from when you were a kid, or maybe you do it with kids now. But you can go large as you need.
So, are you going to need just cores or a complete mold package? Deciding what you need is one of the first things that when you come to us, we're going to be talking about. So if you just need printed cores, there's going to be 3 kinds of cores you can have printed. Solid cores, shell cores, and hybrid cores. Now a solid core is as it says. It's solid through and through sand. You know what you're getting. A shell core has a called out wall thickness and is hollow on the inside, much like the chocolate Easter bunny. That shell core can have any thickness you want. It can be engineered, and it can have a varying shell thickness that is governed by the topology. This can help in crush and in core cleanout in your shakeout room. Okay? Now the hybrid cores are cores that are shell, but inside there is unbound raw sand captivated inside. This is a nice thing in that you can't have metal migration into the core, causing some problems. We've all had that one on a casting. It can also help and eliminate some issues with core cleanout. Because it's loose sand, as soon as that starts breaking down, all that sand just pours out of the casting and clean out instead of if it was solid and you might have to get in there and work on it. The other thing to think about with your cores is the elimination of core assembly. This is a huge and time saver and a quality improvement. No more internal fins on a casting. They can be eliminated. And then there's core vents. No more drilling cores to get a vent and having a straight line. Now you can be a little bit more creative and have your vents work for you in the way that they're going to eliminate gas out of your casting and help with the core crush and collapse and disintegration and get out of it in shakeout. If you're requiring a mold package, you have multiple options as well. First thing to remember is that you don't have a specific flask size. Print your mold to fit what you need. No bigger, no less. The printed sand is somewhat expensive compared to molded sand, so use it wisely. In that regard, all you have to do is put a slab core under the drag if you wanted extra material. On the sides of the mold, you could backfill it with green sand or air set. And you don't need to print a cope just to get riser height or pour height out of this. You can add that with your molded sand as well and just print what you need. The printed molds allow for you to gate and riser rather creatively to get most of your foundry solidification issues resolved. You don't have to worry so much about getting the pattern out of the mold Your main concern is how do you get the metal into your mold. This is a real breakthrough for the foundry. For all those castings that are difficult to do, to get a gentle fill and get all your risers, runners, sleeves, filters, all those added things that you want to put in a mold, even chills can be added. Venting also takes on a new perspective in this, because you can put a vent anywhere in the mold, any way, any shape.
Here's some examples of that casting where Steve is just talking about where there's chills. You can see the chills in the mold. There's multiple pieces. And combining the cores for the complex core assembly. That would have been multiple cores. That way you keep all your accuracies.
Now the only draft you're going to need on a printed mold or a printed core is in the core print area, guys. You still got to have that because you got to have them slide in, and so they don't rub and all the rest of that. But your tolerances can be very tight on your core prints. In fact, if you want, part of the core can be tied right into the mold half. So placement is not an issue. In not having draft requirements for the printed mold or core, your design time in CAD is greatly reduced. And if you have a customer that comes to you to have a casting made and their draft is rather wonky, or it's in the wrong direction or attitude for you to mold it in your shop, this is an option. With no set parting line, you can figure out the best way to get the metal into the mold. And you can simulate your production molding in this. You can simulate either horizontal, vertical molding, floor molding, manual molding. We can simulate anything you want to do to figure out how to make it work before you go to production. That's just for prototypes. For production 3D printed, you can even have them fit into a horizontal or vertical molding. You just print the piece, set it into your core print on your DISA or your Robertson or your Hunter. So creativity by the foundry engineer is going to be the limiting factor on how you apply this to your situation. Keep an open mind of the new technology without losing sight of the traditional way of doing things and how you integrate them. This is where our strong point is that we can help you use the new technologies in a profitable way, not just using them because it's cool and the latest thing going on, but an additive can add to the foundry's bottom line.
So this casting we're showing is actually sent over to Australia, where we, like Steve said, we combined the chills, insulated sleeves. There's actually a A206 casting, so we can do anything like that you guys need. But and then for anybody that's attending this webinar, we are offering a discount if you use the code HPI Webinar 1. Any purchase orders that we receive by June 25th of 2016, it will offer a discount to you. That's on our standard lead times only, no expedited lead times. And then, of course, it'll be subject to what kind of work volume that we have at the time of release, but we are offering a discount. So I guess at this time, any questions?
Thank you, Dave and Steve, for your presentation as part of our webinar this morning. Just a couple of quick notes. If you do have a question, please look to the right side of your screen and locate the GoToWebinar control panel. On it, you'll see a section called Questions. Click on the plus sign and then just type in your question in that space. So that's how we'll be taking questions for this webinar. One of the questions that has come through, and I'll reiterate, is that we did record this morning's webinar. And that webinar and a link to that recording will be passed out to you by the end of this week. So if you do want to review this webinar at a separate time and look at it in on-demand viewing, wait for that email to come with the link to provide you to that webinar. We have several questions for you, Dave and Steve, so I will start reading through them for you. The first question goes back to some of your early slides before we got right to the 3D printing side of things. If you're looking to replace a traditional wood pattern for a metal casting, what is the best of the 3D printing processes that you discussed early to produce a new pattern?
We do this every day. So I'm going to tell you how we do it. We compare FDM printing with CNC cutting. And it has to make sense for one to beat the other in timing and price. So the first way we would say is taking a piece of Ren board, put it on the CNC and cutting a pattern or a core box, and we compare that with FDM and printing a pattern or a core box. And whichever one turns out to be the cheapest is the one that we recommend to our customers.
Okay, question number 2. When talking about 3D printing of sand molds or cores, what type of sand is typically used and what type of sand can be used?
Right now, in-house, we are only printing with an 83 GFN round grain silica sand. I know they are experimenting and working with zircon blends, chromites. They're looking at other consumables, we'll just say even binders between the sand, the base there, and then the binders. But in-house, we are only doing silica at the moment.
While you discussed a little bit size limitations of the castings in the presentation, we did have a question on what are the size limitations of the casting when you are 3D printing the molds and cores?
The large size, there is none, because you're going to put it together like Legos, and the Legos can be the size of your refrigerator at home and weigh what, Dave?
Oh, yeah. 1,500 pounds?
1,500 pound blocks of sand, and if you wanted to make something huge, you can do that. The size limitation for small is that if you have very fine detailed things, you wouldn't want to print that in sand and get things under
it was our definition and accuracy.
Under a 1.5 mil.
Yeah. Yeah, so far the largest mold that we've done is a 80-inch square mold, is 22.5 inches thick. Like you mentioned earlier, we've done some cores where they're bolted together. The core itself was about 100 inches long, and that's longer than the box.
I've got a question. If you wanted to use chills to increase the properties of a casting in a specific area, how would you place those chills within a printed sand mold?
That's going to be geometry specific. There's multiple ways to do it. If you can see the area, you may just leave a pocket to slip it in. If the chill ends up being larger than your feature, we may insert it from the back and have a plug that'll come in from the back and hold it. We may split the mold instead of thinking horizontally where you could slip it in, where you could see it. Maybe we split the mold vertically and you put it in the side. But a lot of it's geometry specific. We've done a lot of different ways. If somebody has that application, by all means, they can email me and we'll help them figure it out how we do it.
Maybe you can talk about shrinkage as it relates to castings. There's a question specifically of when a model is produced, do you need to include shrinkage?
Well, we'll put whatever the foundry uses. If we're provided the model, say from manufacturer ABC, and they are not the foundry, we'll work with the foundry to get the proper shrink. If it's the foundry, then we just double check to make sure they've added the shrink. That's where the communication comes in big. You need your standard foundry shrinks, but we'll work with them to make sure A, it is added, or B, it's not doubled up, and you end up with too large of a casting.
So if you have a model, you can have it made in multiple metal alloys, different, ferrous, non-ferrous, we can pick them, and change all the shrinks, change all the shrinks on CAD and print different molds or core packages to go to different foundries and do it all from a single model.
There's been several questions related to time to secure or to obtain a printed core or mold. But maybe you can talk about what is the build rate and try to talk to people about what the production time is for a printed sand mold or core.
That's a bit of a loaded question. It might be a small mold the size of a couple Harry Potter books put together, or it could be a multiple mold that takes 5 job boxes to build. We can build a job box per day. So it depends. Some of it is we have to fit it into our production schedule, no different than any foundry or core shop, because I mean this is more or less it's just a core shop, it's a different core machine or molding machine. And so fitting it into the scheduling is probably the biggest thing, but if it fits within a job box, normally you can print it within a day. But we're working on a project right now where it was going to take 5 job boxes to do between the multiple mold pieces that had to be assembled and the large core that went with it. So for 3 molds, it was going to be roughly 3 weeks of solid printing.
We consider a 2-week delivery time from the place of purchase order standard delivery. And so that is not topology or shape dependent.
There's several questions related to cost, and while that's extremely difficult to discuss, is there some way to talk about the price of a thing and what are the factors that you guys look at when determining what the cost of a printed mold or core is going to be?
Yeah, pretty much take the bounding box of each individual part. So if you have, say you had a cope, a drag, and a core. If they're flat parted, take the bounding box, the box you would ship it in, freight or UPS. Take that size for each individual piece and multiply that by, get the cubic inches, multiply it by 15 cents. And then there's a standard price to get it to our dock. Now, of course, if it's very small components, very hard to clean, the prices may look very good. The problem is it may not cover our burden rate here in the shop, so that's an exception. But to get a ballpark, that's a pretty decent place to start. But again, they can always email us, and we'll definitely help them out on an estimate.
There's several different questions relating to design and the type of models that can be accepted to produce molds and cores, etc. Could you maybe walk through again the different model types accepted from a design perspective?
Absolutely. We prefer to receive either a step or parasolid model. We can do direct imports on some CATIA versions, SolidWorks, Solid Edge, a bunch of other ones, but a neutral format like step or parasolid is great. Most of the time, an IGES does not import very good. They're not the best for translations, but we'll use that. That way we can build the mold package if necessary. We'd prefer not to receive STLs. Some packages are good at creating STLs and some are not. Then also you have to worry about if they were exported at the right tolerances. You either make an extremely large file that it has a tolerance that's so tight that the machine will never hit it, so it's just a super large file, or it's so low you'll see the facets, the little triangles all over, and you'll have an ugly casting. So yeah, step or parasolid is what we'd really prefer.
Can you discuss the surface finish capabilities with the 3D printed sand molds and cores?
They're typically between 200 and 300 on the RMS. Of course, it's going to depend on core wash and how it's handled there at the foundry. Some of it you may see layering lines because we're building this in layers. If we know that there's an area, that's where the communication comes in. If we know there's an area that somebody needs to watch for, that they want to minimize the layer lines, we can tip it in the box. We need to know that up front to help with the surface finish so you don't see those layer lines. But yeah, typically 200 to 300 RMS. We have some customers getting by far better. Some, I suppose, I'm sure somebody's probably getting worse, but most of the time it's between 200 and 300.
I think we're averaging about 240 is what I'm telling people, and the worst scenario is the dreaded 15-degree angle. That is where the layer lines will show up the worst. So that is what it is. The other thing always to keep in mind is this is printed sand. It is going to have the roughness as if you had a blown core and you scratch the surface. That is your roughness because it is printed. There is no surface that is resin rich and made smooth by that. So it is truly a sand finish with uniform density. And with blown cores and that kind of thing, you get the areas that can be spongy, not strong enough, that kind of thing.
Can you discuss the binders that are used with the 3D printed sand molds and cores? There have been several questions from several different angles. A couple of people specifically asking about the ability to pour steel and any problems with pouring steel with the binder being used.
We ship a lot of these to steel foundries. Right now we're using Furan. Phenolic is, they say, available. My opinion, Steve Murray's opinion, is it's not ready for prime time.
Since many of these printed sand molds and cores are made in one location and then shipped to a metal caster for the melting and pouring, is there an issue with breakage? How is that handled? How is that shipment taken care of?
Truckers, aren't they lovely? And forklift operators. That kind of stuff can always happen. That's out of the control of any of us. We will do whatever it takes if that happens. If that unfortunately happens to you, we will jump on it right away and make things right to alleviate that. But
yeah, there's ways to prevent a lot of that to start with. If it's fragile, you print it in a printed box or like a coffin box, some people are calling it. That way you have great support on the cores. But we successfully ship to North America all over Canada, Mexico, U.S. We've sent multiple molds to both Brazil, the country, and China with no problems. I mean, you can package them for a good success rate, but like Steve said, the truckers and the forklifts, you can't fix stupid. We have had crates show up upside down, and there's really nothing we can do to prevent something like that.
I think we'll do two more questions. There's a couple here. There's been a couple questions talking about mold wall thicknesses or core wall thicknesses. Maybe you can talk into how thick or thin the walls can be and how someone would kind of estimate that thick or thinness of those mold walls, usually utilizing 3D printing, and also what the resultant size of the casting is.
Well, a lot of this depends, I'm sure as everybody realizes, on the size of the casting. How many pounds, or are we going to say how many tons are going into this mold? On most of the things that we're printing, if you have 1.5 inches wall thickness on your mold, you have all the strength and insulating properties that you're going to be required. Now, it's also a matter of safety. So you can in the foundry put us around the mold and backfill it with green sand or air set to give you that layer of protection until you get comfortable on how this works. But if you're thinking about a core and having it collapse, a real easy way to do this is to start out with, as a foundry engineer, what is your best guess? What's your best idea? And if you're saying I'd like a 3/8 wall, fine, let's print that. Let's print a 1/2 inch and let's print 5/8. and even go thinner if you would like, if you're having an issue. But you already know what you're making in your foundries now and what's working. So you already are in the ballpark. Now you can tweak it. And a lot of the solidification softwares are having in them the ability to predict what your core is going to do for collapse, disintegration, movement, all the rest of these things. So that is really into the realm of predicting, is into the softwares. But if you want experience from everyone else, we will be glad to share that with you on what we would say from working on a lot of these.
Last question, if you could talk about the shelf life of the printed molds or cores.
Forever.
Yeah, they stay good. We did a couple studies here. We kept some bars in the sand room, which is a controlled environment. Humidity, temperature stays constant. Ran out of bars about a year into it. We also stuck some out in our warehouse. So we went through a hot, humid summer and spring, and then the dry, arid winter, no problems. All the test bars stayed good. And matter of fact, about 2 months ago, I had a customer contact me and let me know that they finally poured their casting for cores that I had shipped roughly a year ago now. So it was 10 months old, and they used the cores at that time. Those happened to be inside of a printed box. It's how we shipped it all across the U.S. as a fragile core, and they successfully got their casting. So really no shelf life unless the fork truck finds it. But we're big fans of print it as you need it. Don't keep it around. Something will happen to it.
Yeah, it won't be weather related or humidity or something else. It'll be everybody picking it up and looking at it and saying, isn't that cool, and rubbing it, and eventually it gets rubbed away, if you will. If you do have a core and you think it might be absorbing moisture, put it in your drying oven for a little bit and dry it out like you would any other core, and use it. Of course, all sand cores that we make are a little bit hygroscopic. We know that. That's why we don't have them sitting around for a long time. We only make them and use them.
Thank you to Dave and Steve for their webinar presentation this morning, and thank you to the audience for their multitude of questions. We apologize we weren't able to get to every question throughout this webinar, but we will attempt to answer them over the coming weeks because there was a wonderful participation from the audience in today's webinar. Just as a reminder to everybody, this webinar was recorded. You will receive an email with a link to be able to view that recording at a future time. On behalf of Modern Casting and Metal Casting Design and Purchasing magazine, thank you very much for your participation in the webinar. Enjoy the rest of your day.